Hi everybody, and welcome to part C of exercise 7. And this is our last portion of exercise 7, finding volumes of surfaces of revolution. Okay, this time they'd like us to find the volume of the region bounded between three curves, y equals 0, x equals 2, and y equals ln of x, rotated about the y-axis. Okay, so let me first point out that you can kind of picture this region that they're describing by looking at figure B. I'm just going to label the three curves. So there's x equals 2, y equals 0 is on the bottom, and then y equals ln of x, okay, is the curvy part that's there. Okay, and so it's this region that I'm shading that we want to do the rotating of. Okay, in particular, we want to rotate that about the y-axis, so let's draw ourselves a bigger picture of this. Okay, down here. So we're taking, let's start by just sketching the region that they're giving us. Okay, and we want that region to rotate through the y-axis. So our axis of rotation is sitting here. So imagine every point in that region kind of coming out over on the other side an equal distance away. So I'm going to try to draw the mirror image of this. Okay, so it's going to kind of look like that. All right, and as we did in parts A and B, we want to slice this region by slicing perpendicular to the axis of rotation. All right, so if we do that, that means we're going to be slicing left to right in this case. We're going to get a big washer type of a shape. Okay, that looks like that. All right, and as we did before, we'll draw like a little top view of that. Okay, the key again is getting our hands on the radii of that washer. Okay, so if we can measure the inner radius and the outer radius, that's going to allow us to get the cross-sectional area of that slice that we just drew. Okay, so as before, first key question that we need to ask ourselves are the radii vertical or horizontal distances? Okay, well, let's take a look at our picture. I'm going to draw in the inner radius. Notice that that's a horizontal distance, which means that we need to figure out what x is equal to. Okay, if we want to measure horizontal distances, we need to subtract x values. Okay, can we do that? Well, let's start with the point here that's on the curve. What is x equal to there? Well, remember that that point is sitting on the curve y equals ln of x. Okay, I'm just underlining that at the picture at the top of the page. Okay, they give us the curve in the form y equals f of x. Can we solve that for x? Okay, how would we take the equation y equals ln of x and solve it for x? Well, we can exponentiate both sides. So we'll get e to the y equals e to the ln of x. And when you take e to the ln of x, you just get x. Okay, so it would appear then that x equals e to the y. That's the value of x here. And we can tell directly from our picture above that x is equal to 2 at the right side of our region. So that number is going to be a 2. Okay, and oh, by the way, right on the y-axis, okay, this point, we're going to be at x equals 0. So we might just notice that. Okay, so let's go back to our top view picture and see if we can measure these two radii, starting with the inner radius. That's the horizontal distance from the x-axis over to the curve x equals e to the y. So if we subtract those two x values, we're going to get e to the y minus 0, which is just e to the y. Okay, what about the outer radius? Okay, well, that would be the horizontal distance from the x-axis all the way over to here, x equals 2. Can you see how big that is? That's just 2 minus 0 if you subtract. So we're going to get a radius of 2 there. Okay, and let's see, if we write down a formula for the cross-sectional area, it's going to look like pi times the bigger radius squared minus pi times the smaller radius squared. Okay, and that means that our volume integral we can get by just integrating that cross-sectional area. So the integral of pi times 2 squared minus pi times e to the y squared dy. Okay, and only thing that's missing again are the limits of integration. Okay, where do we start slicing and where do we stop slicing? Okay, well, first notice that the variable of integration is y here, so those missing limits should be values of y. Let's go back to our picture here, and I'm hoping that you'll agree that the bottom of our region down here, that's pretty clear that that should be y equals 0 because we're right on the x-axis. Okay, so we can fill in that lower limit without too much trouble. That's just going to be y equals 0. Okay, what about the upper limit though? Okay, well, the top of our region is this point up here. I don't know just by looking what that is. How would we figure that out? Okay, that point at the top. Well, notice that it's the place where these two curves cross, x equals e to the y and x equals 2. So we can take those two curves and set them equal to each other and find the point of intersection. Okay, let's just sneak that calculation in down here. Okay, we'd like to know where x equals e to the y and where x equals 2 cross each other. Okay, we can figure that out by just setting those two equal to each other. E to the y equals 2. And if you take that equation and solve it, just take the natural log of both sides and you get y equals ln of 2. Okay, and so that point up here that we labeled has a y-coordinate of ln of 2, it turns out. That should be our upper limit of integration. All right, so we'll fill that in. And that's our answer. We could maybe simplify it one time just to make it look a little prettier. So 2 squared is 4, and e to the y squared is e to the 2y, if we want to rewrite it that way. Okay, and there's our answer.